I wish I can say that the class is late because the weather is nice. Then that would be a very reasonable excuse. But as the semester progresses, everybody's coming later and later and later. I don't even bring my watch anymore. But unfortunately, I can see the time there. All right. So if you remember, we were talking, we started talking actually about doing maximum likelihood estimation for the parameters in undirected graphical models. So I'm going to continue on that topic, but I realized that some of the algorithms are a little bit more complicated than you guys are ready to take on a sunny day. So I'm going to take sort of a back step today, and I'm going to review this parameter estimation for completely described observed graphical models first, starting with directed graphs, and then I'm going to give you some introduction for undirected graphs, so when we come on the next lecture we can complete the previous notes from last Tuesday. All right, so in some sense the lecture today is elementary. On some other point of view, it's actually more complicated because it involves concepts that we haven't really seen in the homework yet. All right, so we're interested in the following. We're interested basically to learn the parameters of directed and undirected graphical models where we assume that we have all the data we need. There's no unobserved variables. So if somebody gives you a directed graphical model and says, you know what, I have data on all nodes in the graph, can you go and estimate the parameters? And we're interested to go back to the problem we discussed on Tuesday, which is maximum likelihood estimation. So I can tell you what the outcome of the lecture today is going to be, that for directed graphical models, the parameter estimation decouples as one little MLE problem at each node. So basically you can calculate the parameters locally in the graph. So this is very trivial, very effective sort of algorithm to do. For undirected graphical models, for Markov random fields, we already started discussing this on Tuesday. Because of that normalization factor Z, you cannot really decouple it as nicely. So the whole problem needs to come together and compute all the parameters for all the clicks because this Z factor includes all the information. So this does not allow decoupling. Now, there is a very special type of undirected graphical models that is called decomposable models, where somehow we can do MLE locally. And this is what I want to discuss today. And so there is some iterative type of algorithms that compute the MLE solution, and these algorithms are local. Okay? So for directed graphical models, we're going to see the problem is really trivial if we have a completely observed model. For undirected graphical models, it becomes an easy thing for what is called decomposable models. Otherwise, still you can do some iterations, and we will see what type of algorithms we have to discuss there. All right, so I'm going to take a step backwards and discuss the trivial problem first of directed graphical models and see why this is sort of a trivial situation. I realize it's getting hard. All right, let me So we consider a very simple directed graphical model, and you notice all the nodes are observed, right? And so if you try to write the joint probability distribution, of course you're going to have P of x1 given theta 1. So this has its own parameters theta 1, and then you have P of x2 given x1, its own parameters, and finally P of x4 given x2 and x3 with its own parameters. So when you write down the log likelihood, it looks like that. So you can immediately see why this is a trivial problem to discuss about MLE estimation in directed graphs when you have fully prescribed data, because if you look at theta 1, it only comes in this term. If you look at theta 2, it only comes here, etc., etc. So really, if you want to compute theta 1, you can do an MLE problem on the first term if you want to compute theta 2 or the second term, etc. So effectively, the problem decomposes to little optimization problems defined in each node, all right? And each node, you remember, the probability involves the node and the parents of the node, all right? So information that, for example, if you're trying to compute theta 2, obviously the observations x1 and x2 come to play a role. So we're going to have to see, at least for discrete models, how you compute theta 2 given information on x1 and x2. In essence, what the MLE problem becomes a bunch of separate MLE problems defined for each node, and these little graphs that you see involve the node and the parents. Okay? So in many ways you can run this in parallel, and it's, as we will see, there is an analytical solution. It's sort of a trivial problem. So let's, because I'm going to need the notation in the context of Markov random fields, so let's introduce these notations for directed models. So we have a graph G. This is the number of nodes, the number of edges. XU is a random variable affiliated with a node U in the graph. Little xu is a realization of capital X of U. Capital X with subscript C is basically the random variables affiliated with a subset C of the nodes, all right? And this will be a very useful, important notation actually today. And because we use X subscript C to describe the random variables on the subset C, we're going, instead of using X to describe all the random variables, we're going to put X subscript V to describe all the random variables in the graph as well. Okay? So the distribution factorizes basically, this is the fundamental property of directed graphs, as a product of these local distributions for each node, conditional on the parents, and these are the unknown parameters that we want to compute. Okay? So basically, these parameters, if the variables are discrete, they are basically the values that XU takes, let's say, value I, given that the parents take a value J, right? But we just denote the parameters now as theta U, but really, for discrete models, the parameters theta U is the table that gives you the information about this conditional distribution. All right? We assume we have n observations. And here what is interesting, n observations means I have n observations, and each observation involves values of all the nodes in the graph, because everything is observed. Okay? So there is no hidden variables. So again, in everything we have done up to now, when we said we have n observations, we meant some variables in the graph. Here we imply all the realizations are given in the graph, and we have n of those, all right, n observations. Okay, so let's see how we are going to write this. In some sense, what we have is we have n replicas or a fully described probabilistic directed graphical model. You agree? So if I say I give you all of these nodes prescribed, one realization, I'll give you another one and another one and another one. Really, I have n realizations. I have n different graphical models. Obviously, it's not convenient to think that we work with n graphical models. So somehow, when we do the analysis, we will need sort of to take this information and somehow compact it in a way that we can use this probability for one single graph G. Okay. But right now, the way that this looks like, okay, is like that. And so it's a little bit awkward to describe what is going on. So if you describe if you want to describe the nth of this replicas of the fully described directed graph, you're going to have to write it as xv, which is all the nodes at the replical n. Or if you want to do this for a subset of nodes C, then you have to again refer to some replica n. Okay? So it's a little bit awkward to do that. So the observed data set is the values of all the nodes, and we have this given n times. Again, I want you to be sure that you understand this. Each of these are the values of x's everywhere in the graph, all right? And we have n realizations for that. So the likelihood is written as the product over each of these replicas of the likelihood for each graph n given the parameters. So I have n data, I have a product over these the data sets, and then the factorization of the joint distribution over each graph is over nodes, all right? And I put a subscript n here to emphasize that this refers to the replica n. Anybody follows? All right, we're giving n number of observations, and each observation involves the values of all the nodes in a graph. All right? So when I want to write a likelihood, I'm going to have first over a product of the likelihood of these replicas here, 1, 2, up to n. All right? So this is that product. And then I'm going to have to write the likelihood of each of these graphs. I mean, most of the course up to now has been the likelihood of a single graph, but now because it's fully described, I have a likelihood over n replicas of the graph. A little bit different. Okay? So, and this distribution for this replica n, it is written in the classical way as the product of the xu for every node u given the parents, all right? And theta u are the parameters that, that define that conditional distribution. So we take the log likelihood, all right? The products become summations. It looks like that. Can you see now immediately why this MLE estimation decouples? Can you look at this equation? I don't read anything in the text, etc., so we can move faster today. And tell me, looking at this equation, what information from the observations do you need to compute the parameters theta u that come in the conditional distribution of xu given its parents? So what information, how do you, maximize this with respect to theta u for a given u? In how many terms in this double summation theta u comes? N terms, okay, and only one of the summations on u. All right? So what are the sufficient statistics basically from the data, or at least what information looks right now from all the data that is going to be essential in computing theta u looking at this? The observations of the node xu in the n replicas that we had, and also the information on the parents of u. There's no other term where this thing is coming in. Do you see that theta u only comes in this, the parameters that come in this distribution, right? So you have summation of many of these distributions. So theta u will only be in all these terms n where we have the u here, u and the parents of u. They're all decoupled. Okay? They're all decoupled. All right. Now, we will see that if this distribution is in the exponential family, right? Actually, we can easily compute sufficient statistics, all right, that for any n, basically. Okay? So let's see how this is going to happen. All right. So remember, so the notation now is going to get a little bit complicated, and I need this when throughout the lecture today. So we have n observations of all the nodes being the graph. Okay? So, let me introduce the following definition, all right? So, little x, you remember, is realizations with a subscript v. Here is the realizations of all the variables. So m of xv is the number of times that on my data set I see this realization little x with subscript v. Remember, I'm working with discrete variables, right? So every x takes a finite number of values, and I'm taking a collection of all the variables. And I'm asking for this collection, little x is realization of all the variables v. How many counts, how many times that collection of all the variables happens on the data set that I collected, which is this n times, you remember? And what it is it is the summation of these delta functions, or indicator functions if you want them even better, and this gives me 1 every time xv coincides with xv subscript n. You agree? This is what I have observed. So if you give me a bunch of realizations of all the x's, obviously the number of counts, how many times in my data set this happens, is the summation of this. You know, sometimes I'm wondering if anybody's sleeping, and then I realize somebody looks there, somebody looks there, somebody looks up there. So, we're okay? Yeah? Yes? All right. Okay, so this, again, x subscript v is the realization of all the variables in the graph. You give them x1, x2, x5, x55, whatever you have, the number of times, the number of counts that you see this in your observations is the sum. Now, I am going to introduce the notation for partial counts over a subset of the variables. And I want you to look very carefully on this equation and convince yourselves that you understand it. So we introduce m of xv, the number of counts in my data set of this observations x1 to xv, all right? And now to define a partial count over a subset C of all my nodes, okay? What I have to do is take this and sum it over all the realizations in V minus C. So I give the realizations of C, and I can compute this partial count, all right, or marginal count by taking this and summing everything except x subscript C. If you think, right, you are given these values, and you have lots of other values, and you say, I'm going to sum for all other possible combinations of all the other variables, and that will give me the count of xc. For example, if I have 3 variables, all right, and m of x1, x2, x3 is the number of times in my data set that capital X1 takes the value little x1, capital X2 takes the value little x2, capital X3 takes the value little x3, to define the number of times that in my data set I have capital X1 taking the value little x1 and capital X2 little x2, what I have to do is take the count for all the variables and sum x3. Make sense? Yes? All right. So, and similarly mx1, I can sum x2 here, or I can sum x2 and x3 on that. Okay? So what I want you to remember is, this is the count, m of xv, for all the variables, and this is a partial count for a subset of the variables, and this will be an essential thing, right? Because we will, you will see shortly why, as we try to solve the MLE problem. Now, look at this equation and tell me, this is for the example, all right? But effectively, if I take m of xv of all the variables, and I sum for all possible combinations of xv, then I have to get capital N there. Right? Here I take all possible realizations of my variables, but I have only n observations, so this sum has to be equal to capital N. Okay? All right. So let me introduce the last notation, basically, then we're ready to go. I'm going to introduce a partial count for the family of a node U. Okay? So the family of a node U is basically U and the parents. All right? And I denote this as P of U. Okay? So take some realizations of the nodes that belong to this family of node U. Obviously, the number of times that you see this in your data set is the partial count, which is computed if you take M of all the realizations of XV and you sum for all values in these nodes except the values that belong in the family of the node U. You see that? So this is the number of counts that you see a node U take some values and the parents take some other values. Okay? You can compute this by taking the total count over all the nodes and summing everything but the nodes that belong in that family. All right. So let's, I don't have to go through all of this. So I'm looking on the equation on the bottom, all right? So we're looking for the likelihood of the observations I have, and I'm guessing there I should put most probably a D, okay? It's on slide 11. This is fine as it is, but you know it's better to put the probability of the observations given the parameters. So do you agree, and we wrote this equation before, that this is the product of the likelihoods over these n replicas? You remember, every replica n, we know all the nodes, okay? So I have the product basically over n graphs, right? So this is little n, and this is the likelihood for each graph n of observing the data that I have given for that realization, okay? So now look what I'm going to do. I want to get rid of this index n and this product in n, so I'm going to start doing some algebra. So I am going to write this probability for this replica n. I'm going to write it as this product, and I want you to look and tell me that you understand it. All right? So what exactly have I done here? Remember, in this term, all right, I have a particular set of realization of all the variables, all right? X subscript v, comma n is for the n replica. I give the values of all the nodes, and I write this as the following. Take basically the probability of observing little x subscript v for all possible values of xv, and only count those values of xv that are equal to xv, comma n. We have done those tricks actually before. Okay? All right? That's this equation on the middle. And then for, notice that the probability basically of having the realizations of all the nodes, okay, given the parameters is basically the product of the probabilities of the parents given, I mean of the nodes given the parents. But what is important is, notice that by doing this trick here, there is no, I only work with the probability of one model. This is very important. The subscript n has been eliminated. Here, right, when we start playing, right, so we had the probability of x v comma n. Here there is no anymore n. The n has gone up to that delta function. So we work with the probability, the joint probability of one graphical model alone, not of the n replicas. Okay? So let's put all of this in action. And we're practically done, I think, with this slide. Take the log of this. So this product is going to become a summation. All right? We don't like this comma n there. So this term is going to become a summation. The delta function will come down, and then we're going to have log of p of xv given theta. This is nice because this is the probability, the log likelihood for our generic graph, right, does not involve any n. And now, notice, if I take the summation here in n, what is this summation giving me? What is this summation according to our definition? You know, I go through basically, okay, so this is for all possible configurations, and then, you know, what I do is, for each xv, I am checking how many times that xv has appeared in my data set. So isn't this the counts of mxv? Right? Okay? So basically, if you look at this, there is absolutely no n here. I work with one graphical model now. There's no replicas of models, etc. I work with one graph alone, but somehow that n has been integrated in the number of counts that I observe x subscript v. Okay? So let's continue. Right? So the log likelihood of all my observations is this again. And I write this probability as log. I factorize this over the conditional probabilities of each node given the parents. And I forgot to mention that conditional probability, I basically, because we work with discrete variables, I write it you know, in parametric form as parameters theta that belong to the node V, and they are functions of the data of the node V and its parents. This is just a notation. I could have written explicitly this as P of xv given x of its parents, comma, theta v. But for a discrete distribution, the parameters are really the values of a conditional distribution given different values for the node V and its parents. All right? So this is basically from the factorization of the directed graphical model. So, okay, there is the product becomes a summation, the logs goes inside, and I start doing tricks now. So let's see, I take the summation of V, I put it outside, I take the summation over all the realizations of all the nodes, and I split it in a summation over the realizations of the family, and the realization of all the nodes minus the family. Am I allowed to do that? I split this, right? This is a summation over all possible realizations of all the nodes. And I split it over the family of node V and everything, you know, except the family of nodes V. And, all right, look now at the inside summation. What is the summation of this on the total counts of xv? We introduced a definition, it was our second definition of counts. So if I take this summation here, what is it? If I take f of xv and I sum everything but the family of v, what do I get? The partial count of the nodes in the family of v. All right? So now can you see why immediately the problem, the MLE estimate decouples, and why I can compute the parameters affiliated with the conditional probability of node V independently of all the other parameters? Can you see that? This decomposition here, right? Okay, separates this, right? This is for each node V. And for each node V, I have this summation over all possible realizations of the values of x in the family of V. So basically you can immediately see that this parameterization only comes once for each node V. The problem is completely decoupled. So we want to compute these parameters. So obviously we're going to maximize this, but to maximize it, we also have, so when we decouple it, right, we're going to maximize each of these terms separately, okay, because these parameters appear only in this term, but we need to be careful because since this is probability, is conditional probability, when you sum in xv, you have to get equal to 1. When you have the probability of xv given its parents and you sum on xv, it better sums to 1. Okay? So basically, you have to put a Lagrange multiplier, and you want to compute the MLE estimate for the parameters that define this conditional distribution. You have to maximize that, and the answer is immediate, and it's actually obvious. It says that the MLE estimate of theta subscript v, and remember, really, this is the conditional distribution of xv given its parents. So you put some values for xv, some values for the parents. That's what we're looking here, is the partial count of x in the family divided by the partial count, okay, of x corresponding to the parents of v. Does that make sense? So basically, to calculate, let's say if you have a node x1 condition, let's say x2 condition on x1, and you want to calculate the parameters of that. So what you have here is, you have m of x1 and x2, all possible counts of the values you have observed in your data set for x1 and x2, divided by the observations that you had for, in the particular case, if x1 is the parent, basically for the counts of x1. Is that sort of an expected answer? Right? I mean, if you think about it, right, I mean, this is the obvious answer, and usually, if you don't get the obvious answer, you're doing something wrong. Again, this is for discrete distributions, okay, and this is what you get. So the bottom line is this MLE estimate for directed graphical models decouples, okay, and you can solve these problems basically for each node separately, and these partial counts that you get is the sufficient statistics that you need and contain all the information relevant to this local estimation, MLE estimation problem for node V. So all these estimates are independent for each node of V. This is very nice. Now, I know I did this in the class in the fall. Someone will say, you know, if you try to do discrete models and these probabilities, right, are very high dimensional, so you basically need a very high dimensional table to describe this. Obviously, that is not going to be very practical. I mean, if xv can take 5 values, this can take 20 values, you know, you're lost. Okay? So what you usually do is you approximate this with a generalized linear model. So you basically you link this distribution with fewer parameters through a generalized linear model. And so in we have shown, and you can go and visit one of the lectures from the fall semester, and I think Murphy's book has this as well as an example. You can show, so in this case, these generalized linear models corresponding to each node V are decoupled. So you can compute the parameters of each of these models separately for each node, and you don't have a nice solution in terms of counts the way that you see here. So you have to solve an iterative reweighted least squares problem. Okay? So basically what you get is a weighted least squares problem that you solve iteratively, but you can do this algorithm in parallel for each node. So in essence, you know, the problem still decouples even if you have a much more complicated expression for this conditional distribution. Okay? The only thing I want you to not forget here is, right, that it says for completely observed data sets. All right, so you have the graph. Everything is prescribed in the graph. There are no hidden variables. Can you guess if you have hidden variables? Since I said something in the lecture last time, and we're going to come back on it next week. But if you have hidden variables, how do you do you have any algorithms at hand that you think the same idea can be applied? So basically, somehow you can do some iterations and apply sort of the same algorithms. What that algorithm will be that will allow you to work with hidden variables, unobserved variables? but this is MLE. So how will you do MLE when you have hidden variables? How do you do MLE when you have hidden variables? How do you do MLE when you have hidden variables? There's only one algorithm, you know, and the guy will, you know, will not be happy that you don't know that algorithm. EM, expectation maximization. You don't remember expectation maximization? No? No? All right, you know, life is what it is, and, you know, and you move on, okay? So, expectation maximization. All right, so you do expectation maximization. All right, you leave it there. Okay, so we're going to go back to the problem we were discussing on Tuesday, and try to see how we actually can do MLE on undirected graphical models. We will see the problem does not decompose. Okay, and it is a little bit complicated, mainly because of this normalization factor Z that couples all the parameters in the graph. Okay. So again, fully observed data sets. Okay, and we have n replicas as we started before, but somehow we would like to get rid of these replicas and work with the probability of one undirected model. So we will need to borrow some of the notation we use for directed graphs. That's why I inserted those slides. But this is the main difficult problem we need to address. Okay. So for one graph, if you give me the realizations of all the variables in the graph, right? This is basically one of the normalizations Z, and the product of these potentials defined over clicks. And for the discussion today, actually, I'm not assuming anything about this click, so you can use whatever you want, so they don't even have to be maximal, okay? So these are potentials over clicks, not necessarily maximal clicks. The normalization factor is basically the numerator here, where you sum over all possible configurations of XV. And my notation is identical to what I used before, so let's go again, all right? Please ask again if it doesn't make any sense. The probability of all the observations is the product of the likelihood for each fully described graph, right? XV comma n is the data for the n replica of the graph where I've given all the realizations, right? Okay, and I write each of this as the product over all possible configurations of one graph now, where I use the generic graph G, and I use the likelihood of that for some realizations XV, and then to get the replica n, I put a delta function on the exponent. Right? So when XV coincides with XVN, I'm in business. Right? But by doing this, effectively, I don't have anymore to deal with this XV comma n. Okay? I'm going to deal with one probability model for my graph. I mean, why having n replicas? This is it. This is what I want to work with. Okay? Not this. This is not good. Right? I mean, they're the same, but this is much more elegant. So the log of this is, so I'm going to take logs here, summation in n, and then I have xv, so summation on all configurations of xv. I have p to an exponent, so the delta function will come in there. And again, what is this? This is my counts of xv in my data set. All right? This is up to now, it's identical with before, nothing new. So here is the difference then. And I think this is what we were, where we finished on Tuesday with slightly different notation. So now what we do is we plug in this factorization from my undirected graph. So this is log of 1 over z over the clicks on my graph of the potential psi c. And immediately you appreciate the problem. Yes, you get a summation over the logs of the potentials, but also you get the log of z. And that's the main headache in all undirected graphical models. Okay. Now you get summation of m of xv, and you remember what is this quantity equal to? This big summation here, what is it? If you take the counts of all the variables, the realizations of all the nodes, and you sum for all possible xv's, what do you get? N. All right? So this is what you get. Okay? You get summation on xv, summation over, maybe this is the set of all the clicks, so maybe I should put here a summation over C. Okay? Slide 16, so we need to correct that. And so this is, and then you know what I do is I'm using magic and I write the equation on the top in the equation 2. And I want you to tell me how equation 2 came there. I use ideas of partial counts, but you have to tell me how from that you went to that. What have I done? Obviously, I haven't touched the summation over the clicks, so it's there. What have I done on xv? That summation on xv. What have I done on the summation on xv? I mean, I see here m of xc. So basically, that summation on xv, I wrote it as a summation on xc and another summation of xv minus c. And when I sum everything but c, this total counts m become the partial counts of xc. You see that? So basically, why have I done this? Because I only want to see if I can compute the parameters of this click, right, separately for each click. So I'm trying to isolate click C. Right, so you can see here, you have a summation over the clicks, okay? A summation over the realizations of the variables of each click. Here is the partial count of xc, log of psi c, this is a function of xc. So immediately you can appreciate that there is some decomposition there similar to what we have for directed graphs, but z involves all the parameters in the model, so we are ruined. So that's the main complication, basically, and it is a problem very fundamental, not just in machine learning, but very fundamental in statistical mechanics and other areas. Okay? All right. So this is, what do we do? All right. So we need to start doing some algebra to see what is going to come out of this, right? And I am going to try to optimize with respect to each potential psi c, okay, for each click c. So here the idea is we're working for a given click, so the nodes in that click are fixed, all right, and the configuration in that click is fixed. But what is not fixed is the potential. Right? We're trying to find parameters, and in this case, parameter is a function. We don't know what that function is, but the realization xc is given, and the click c is selected. Okay? So the only unknown that we can maximize here is the potential psi c. Okay? So we take derivatives with respect to psi c, and immediately this is similar with directed graphs. This decomposes. So we're going to have the partial counts of xc, 1 over psi c. Remember, when you look at this term, right, the psi c comes only in one term. All right, it comes only in one term. Okay. So this xc here is fixed, okay? And so for a fixed realization of the variables xc, we only have one term psi c of xc, and we take derivatives with respect to that. So m over 1 over psi c minus n times the derivative of the log. And now we start getting headaches because log of z, the derivative would be 1 over z times the derivative with respect to psi c of xc. And z is written, you remember the z is the normalization, So it's written like that. Product of all the potentials, and then I sum all the variables. And because I don't want to confuse, since I work with a given xc, inside this z definition I put an x curly, right, because I sum all the x's here out. Okay, all right? So this is the equation that we started with. So m over psi c. Now I have done a little bit of a trick, right? So can you appreciate what trick has been done on the second line? I wanted to move that summation on curly x outside, just to simplify my algebra a little bit. So what's the trick here? To move the summation of x curly out, I need to be sure that on this term, wait a second, what happened? Yes, all right. So I need to be sure, you remember here this derivative with respect to psi c for a given xc. So I need to put a delta function there to be sure that I don't ruin things. Remember inside here, I integrate all the x's out, that's why I put x curly. So if I want to put that summation outside, I better have a delta function here to be sure that here I only differentiate with respect to psi c of xc. Okay? All right? So this comes there, minus n1 over z, delta function. And now, inside here, I have the product of all the psi's on every click, all right? And you notice here this now became x curly of c, okay? And this is also curly. So you remember, if I have the product of this and I take derivatives with respect to one term, what I'm going to get is the product of all these potentials except potential c. Right? You have all the terms and you differentiate, one disappears, and you get the product of everything but c. And obviously now what I'm going to do is I'm going to multiply with this term and divide by that term. So that way, inside this here, I am going to get again my whole distribution for x term. Do you see that? So what I did is here, I will multiply with psi c of curly xc and divide by that. So the term that I multiply together with this will give me that. All right? So, and now, since I have done my algebra with this little trick, I can push the summation inside, plug in xc here, all right? And then what I get is, I get, from here I'm going to get p of x curly, all right? There is a delta function inside, and I want you to tell me the summation, what will it give me? So here, this is all the variables in the graph, right? And you say sum for all possible configurations, but be sure when you are on the variables of click C, fix them at xc because xc is fixed. So what did you get out of it? What did you get? P of xc, and what is P of xc? With words? What is P of xc with words? What is the name? I mean, here, this P has v variables, right? There's all the variables in the graph. Now, I integrate all the variables out except the variables on the click C that I fixed them on the realization xc. So what is P of xc? It's the marginal corresponding to the realization xc of the nodes in click C. That's very nice. All right? So this gives me the final result that looks as follows. The derivative of the log likelihood of all my observations is the partial counts on my data set of xc divided by this now optimized, right? We need to figure out what will lead us. The potential on click C computed at xc. Right, up to now xc is fixed, minus n times 1 over psi c of xc, and this is the marginal over the click computed at xc. So this cancels out, that cancels out, and what I get is the this is this is basically this value, that's the MLE estimate. So the MLE estimate for the marginal over click C, computed the realization XC, is M of XC divided by N. An amazing result. And what is M of XC divided by N? What is on the right hand side? What name will you give this? This is the partial count of XC. So M of XC divided by N is what? What name will you give it? Is you count how many times in your realizations you have seen the variable XC, capital XC, to take these values of little xc. So what is this M divided by N? What's the name we should give to it? You know, out of the N data sets, you have seen these combinations of XC M times. So what is M over N? For discrete distributions, how do you call that? Spell it. I can see you fighting with it. So what's the word? Frequency, okay, you're close, all right? Another word similar to frequency. And in the alphabet, it's very close. One starts with F and another starts with E. Empirical distribution, right? So basically, the optimal marginal is equal to the empirical distribution. So basically, what we have done is the model marginal agrees with the empirical marginal. It's an amazing result. If you think, right, we have done no assumptions, anything, not even, we haven't even said that the clicks are maximal. But the maximal likelihood estimation for this function psi somehow implicitly implies that the model marginal for each click has to be equal to the empirical margin. Now, the bad news, right, our objective is to find the potential psi, and that information is hidden because you remember the potentials are not marginals. The potentials are not marginals. So the idea here is, it doesn't matter, this algorithm, this derivation tells you, I don't know how you're going to compute these potentials, but whatever you do, if you want to call this an MLE estimate, be sure that the model marginal coincides with the empirical margin. But it doesn't tell you what those psi's will be. There's no information on this equation. Okay? And why there's no information? Because unfortunately, when we took the gradient, these two psi terms cancel out. But don't worry, this psi term, don't you think is contained inside the marginal of P of XC? It's implicit in there, right? Because that marginal connects the nodes of click C, and what connects it in the factorized distribution is really that potential. It's just that the potential is not a distribution, all right? So this is what you get. So we will obviously need to figure out a way to extract the potentials with some algorithm in a way that satisfies this condition, so we can call those estimates MLE estimates. All right. So let's figure out a trivial algorithm on how we can extract these potentials, starting first for a very particular set of undirected graphs, and then we will extend this to arbitrary undirected graphs. So, I'm using a simple here example with 3 nodes. I am writing the probability of xv as one potential over x1, x2, and another potential over x2, x3. So these two potentials basically share node x2. So obviously there is an empirical count of x1 and x2. Remember this p curly is empirical count. So there is an empirical count x2 and x3. And you know what? I am going to give you what what the solution will look like for the model, for the MLE solution, okay? What's the MLE solution? And you can tell me if I'm right or wrong, okay? I'm guessing it now, all right? So I am going to tell you that the MLE estimate, okay, is given by this empirical marginal, x1, x2, times this empirical marginal, but divided by the empirical marginal of x2. And can you do some checking and tell me that this satisfies the condition that we had before? So really we can call it an MLE estimate. So I'm just throwing it there and I say, this is the solution, and I want you to tell me that that solution is actually satisfying this. So can you tell me that that's the case? So you remember, the MLE equation is that the model marginal has to be equal to the empirical marginal. So this is my model. I postulate this is the model. Take the marginal, let's say, of x1 and x2. All right? So take from this the marginal of x1 and x2. What do we need to do to get the marginal of x1 and x2? From this approximation here that I postulate that may be my answer, to get the marginal of x1 and x2, what do I need to do? How do you marginalize? Sum on x3. So when you sum on x3, what will you get here? They will cancel out. So you get that the model marginal of x1, x2 is the empirical marginal of x1, x2. Do the same thing and marginalize, let's say, on x1. If you marginalize on x1, this will give you the empirical marginal of x2 will cancel out with this, and then you get the empirical marginal of x2 and x3. So this satisfies actually all the properties that we stated there. So it is the correct solution. So effectively, how did I guess the solution? Here is the trick. What I did is I took the clicks that I had on my problem, like x1, x2, x2, x3. I took the empirical counts over these clicks. So these are my empirical marginals. And because these clicks have an overlap over this node x2, I divide it by the marginal of node x2. Okay? So the graphs where you can actually do this type of things are called decomposable graphs, right? And so here is one decomposable graph, right? Okay? And here is one graph that is not decomposable where you won't be able to actually do this trick. So this idea of starting with empirical marginals and try to guess what the solution will not actually apply to this problem, okay? And the reason is not because this has a loop, all right? This has nothing to do, at the end of the day, you have a loop here, but it has to do with the fact that this, what you see here, is not a decomposable graph. So what's the definition of a decomposable graph? A graph is a decomposable if you can divide it into three disjoint sets, A, B, and S, where S separates A and B, and S is complete. So all the nodes in S are connected, okay? So if you look on this graph, I can divide it on this node, and that node, and obviously this S node here, X2, separates X1 and X3, right? And I can do the same thing here. I can divide this to be the set A, this node X4 to be the set B, and X2 and X3 that are connected, they separate X1 and X4. But if you go to this graph, you can try, if you try to define A, B, and S, you're not going to succeed unless you actually add extra edges from this graph. All right? Unless you add extra edges to this graph. And let me tell you, and you know, I know we're not going to be able to discuss this in this course. You remember when we do, in the very early part of the course, we were doing graph elimination. So imagine that you do graph elimination here, right? And you start eliminating any node. It doesn't matter, they're all symmetric. So if you eliminate X4, what do you need to do to the next step? You need to add an edge, all right? So this idea of decomposability for these graphs, it is directly linked with the graph elimination algorithm, all right, hand to hand, and actually at the end of the day, they're directly linked with the junction tree algorithm. Okay? So, if the graph is decomposable, the solution is trivial, all right, and there is more discussion in the notes, okay? Okay, so it's easy. If the graph is not decomposable, basically there's nothing you can do with the present form of the MLE estimate, so we need to do something better. So since the time is clicking, so let's see what we will do if the graph is a generic graph and we cannot use this decomposability basically of the graph. So we're going to do an iterative algorithm that's called iterative proportional fitting. Part of these notes are contained also in the lecture on Tuesday, but we're going to come back so we can finish the course. So let's see what this algorithm is. So you remember that when we took the gradient of the log likelihood, we basically, the gradient was this term minus this term. You remember we said that psi and psi's cancel out. So now what we're going to do is, okay, there is psi also inside this model likelihood implicitly, right? So what I'm going to do is, I am not going to get rid of psi c, but I'm going to create an iterative fixed point algorithm using this equation as follows. What I'm going to do is, I am going to use, so this is my empirical marginal, all right, is there. I am going to divide by my previous guess of the model marginal, which is this, at iteration t. I am going to multiply with my estimate for the potential at iteration t, and then the other term on the other side, it will be my new update at time t plus 1. You see what's happening here, right? I took this to the right-hand side, I push everything to the left, all right? So this thing on the right-hand side will be my t plus 1 update based on the estimate of the previous time times the ratio of this empirical marginal divided by the previous estimated marginal on click C. Now, for those who have done this in numerical analysis, it's not like you take every equation, you divide by some unknown, and you do a fixed point iteration, somehow this thing converges. There's absolutely zero guarantee that this will actually make any sense. Well, in the notes, and I don't know how much time we have, there is a proof actually not only that this is working, but it actually maximizes the log likelihood. So it's actually a coordinate ascent algorithm as well. Okay, and so let's see how this. So this is how this thing works. All right. I am not going to go through the proof because the clock is 1:34. But let me tell you two things that the relation is actually trivial. There's just algebra. There are two things that happen when you iterate with this algorithm. Number one, the marginal at every iteration is equal to the empirical marginal. So you know what it means? As you iterate, you satisfy the MLE constraint. So it's not like you keep going and hoping that at the end you will satisfy that the model marginal is equal to the empirical marginal. At every iteration you satisfy that. Nice. And second, the normalization factor does not change as you do iterations. Okay? So, and again, the proof is actually, it's rather trivial. And I want to give you, so basically, this is the MLE property, right? So at all iterations, your model marginal is equal to the empirical marginal. The Z doesn't change. But I wanted to give you a version of this algorithm. This is what we derived. You can actually show, this is very important, you can show from this equation, you can show the algorithm takes the form that you see on this equation on the middle, okay? And I'm going to rewrite this equation in a form that sort of, you can, with some intuition, you can come up with it without any mathematics, okay? So, I didn't give you a proof of this. You can show, the proof is actually 2 lines, but with this algorithm, you can show that the probability of xv, right, on the whole graph at iteration t plus 1 is your estimate at iteration t times the empirical marginal at click C divided by the model marginal at click C. I mean, you can, you know, when you work on this, right, you really operate on click C, so you can appreciate why I can substitute this size here with a whole probability distribution. Because also the Z doesn't change. So it's not like you go from t plus 1 to t and the Z is going to ruin you because the algorithm keeps the Z constant. Okay? So I'm going to take this equation and I'm going to rewrite it. Okay? So what I'm going to do is I am keeping this empirical marginal there, and I am taking this divided by that, and I'm going to write this at iteration t, and I'm going to write it as the conditional of xb minus c given xc. Do you agree with me that this divided by that is the conditional of xb minus c given xc? I mean, if you are going to expand, right, this will be the joint of this and that, which is that, divided by the model marginal xc. Nothing new. Now, why am I doing like this? This is how the algorithm looks like, all right? And there is intuition here. What do? You're actually changing the potentials on click C through the marginals, you know, on the variables on the nodes on click C. So basically what this equation tells you is, you know what? To estimate the joint probability distribution of step t plus 1, use the previous conditional where the variables at C are not updated, and the only thing you do is go and update the marginal on xc. All right? So you keep the previous, again, xc here. This is the conditional from the previous model times the new marginal, which is basically, it is, so you update basically the marginal on xc with the empirical marginal. Very trivial algorithm if you think about it, and this algorithm is applicable sort of to any type of undirected graph. It doesn't have to be, you know, decomposable, you know, haven't really said anything about the clicks have to be maximal, so it's, and again, you can see on the slides the details. There is a proof actually that this increases as you iterate the maximal likelihood, and it will give you the right solution after a few iterations. By the way, if the graph is decomposable, I think you do this in one iteration, it converges to the right answer. Yep. What did I say before? That the whole thing is directly linked, actually. Yeah, exactly. Okay. Well, so the junction tree as an algorithm is basically the most general algorithm, right? But so the two things are directly linked here. Okay. So the graph elimination algorithm, the junction tree algorithm, what you see here, it's basically theoretically have the same origin. All right. So there is a proof that this algorithm is a coordinate ascent algorithm, and I'm going to give you something that somehow, when I was looking at you know, Mike Jordan's notes that I gave you some time ago, he has a derivation of this IPF algorithm that is very interesting, using sort of one identity we have never seen, and most probably very few people use, okay? And something we have discussed, at least we discussed for those who took the course in the fall. So let me give you, you can derive all of these things using a minimization of an appropriate KL divergence distance. And the KL divergence that you need to minimize is basically the distance between P of x given theta and the empirical distribution P of x. All right? And what you need to do is, you can show, by the way, so let me state the things that you should know by now. if you want to maximize the likelihood, this is equivalent to minimizing the distance of P of x from the empirical distribution pk of x. That's a standard theorem, all right? If you want to maximize the likelihood, the derivation here is the same as minimizing the distance from the empirical distribution of x. That's fact one. Fact two, this Kullback-Leibler distance d between some distribution p from another distribution q, where I split the variables in two sets a and b, can be written down in a sort of very nice decomposition that is given by this second line here. So if you need a distance between p of xaxb and q of xaxb, you can write this as the distance between the marginals and the distance between the conditionals average over xa, all right? Okay? So what I'm going to do is, so this is not something you see often, but it comes very handy in our problem, because if you use this idea that maximizing the likelihood is the same as minimizing this distance, and if you write this distance using this equation, you actually get the same answer as what, directly doing the algebra that I showed you before. And here is how this KL distance manifests itself in our problem. So what I do is, to minimize the distance between the model and the empirical distribution is the same as, we have to write this distance as the distance between the marginals, and I'm using the marginals of click C between the model and the empirical, and then I have this average that involves the conditionals of all the other variables given xc. So the only term in this equation that I want to minimize with respect to xc is this term. There's no xc here. xc has been integrated out. So how do we minimize the distance between this marginal and this empirical marginal? Obviously this has to be equal to that, and that's what we proved before. So there is a proof in one line, right? And again, you never know where and how things will be useful, but this nice decomposition of the KL, it's actually very handy because it gives you an answer, no need to take gradients and, et cetera, et cetera. Okay? What you can do is you can use ideas from stochastic gradient descent, so we can finish. So rather than doing this fixed point iteration algorithm, you can introduce some learning rate and rewrite this gradient equation. This is the gradient, so you can put some learning rate rho, and you can keep doing updates in a stochastic gradient ascent format. If you apply this algorithm, not what we discussed today, the only thing is you need to be careful because the normalization constant z has to be recalculated at each iteration. It doesn't remain constant. All right. And again, if you have latent variables, basically what you need to do is both for directed and undirected graphs, you can apply exactly the same techniques we discussed today, but you apply them at each iteration of the EM algorithm. So really, you can do this for any problem with hidden variables. Very simple way to estimate the parameters, assuming that you have complete data description. All right. Do we have a recitation on Friday? All right. If Shuvik says no, we have no lecture on Friday. Okay. I'm going to email you if we're going to have a lecture next Friday, but there's no lecture on Tuesday and Thursday. Okay? All right? So we'll see you next week.